A demonstration of solving a polynomial inequality. Here is a vocabulary term that will be used in this presentation. It's called a critical number. A critical number for an inequality statement is a value, we'll call it C, such that f of C equals 0 or f of C does not exist. Now, a guideline for algebraically solving polynomial inequalities is given here. Our first step would be to get 0 on one side of the inequality. And then our second step would be to combine like terms and determine the critical numbers to the polynomial. This would be the real solutions. Okay? Our third step would be to determine the sign, positive or negative, for each interval the roots divide the number line. Multiplicity of roots and end behavior, or the tail end test, are useful here to avoid calculations. And then our final step would be to report the solution based on the inequality. So our example is going to solve the following polynomial inequality. X cubed minus x squared minus x is greater than -1. Our first step is to get 0 on one side of the inequality. So here we add 1 to both sides, and we have x cubed minus x squared minus x plus 1 is greater than 0. Now our second step is to determine the roots to the polynomial, and some people may refer to this as solving the associated equation. Now on this slide, the steps that I have done are also written out in words so that you can kind of follow what I did. So starting with our inequality, x cubed minus x squared minus x plus 1 greater than 0, we've changed that to the associated equation by saying x cubed minus x squared minus x plus 1 is equal to 0. We're going to find those critical numbers. Now, the next step, I rearranged some terms. I switched the locations of x squared and x. And what this enables me to do is it enables me to factor x out from the first pair. That's why I have x times the quantity x squared minus 1. Then the next step is to factor -1 out from the second pair. So I have x times x squared minus 1. And then when I factor out the -1, I have -1 times the quantity x squared minus 1. Now that I see both of these terms have an x squared minus 1 factor that is shared, I go ahead and factor out that x squared minus 1. So now I have x squared minus 1 times x minus 1. That was what the numbers that were multiplying the x squared minus 1. X squared minus 1 is a difference of squares. So I go ahead and split that up into x plus 1 times x minus 1. And then I have an extra x minus 1, this one here, just kind of following the arithmetic and putting it down next to the difference of squares factorization. Here I notice that I have x minus 1 times itself. So I use the definition of exponent, and I can write my factored form as x plus 1 times quantity x minus 1 squared, and all that's equal to 0. Now, the factor theorem tells us that the roots to this polynomial are going to be -1 with a multiplicity of 1, because that's the power on the factor, and then x equals 1 with a multiplicity of 2, because that's the power on its factor that is associated with its solution. Our third step is to determine the signs for the intervals. Now, here we can use multiplicity of the roots and end behavior. So the root, -1, had a multiplicity of 1. And that means that it's going to cross the axis. When a polynomial crosses the axis, it means that there's a sign change. And a sign change is very useful when solving inequalities because it tells us that it's going to change from either positive to negative or negative to positive from one interval to the next. Our other root at +1 has a multiplicity of 2. And that means it's going to bounce off the axis. And that means that there's no sign change. And again, this is useful when it comes to solving inequalities because that means that there won't be a sign change, which means the sign will stay the same on either side of that root +1. The end behavior allows us to get our very first interval and our very last interval. We can get the signs on these directly. Now, our degree was odd. We had an x cubed polynomial. And the leading coefficient was positive. And that means that my graph is going to start negative and it's going to end positive. So my very first interval from negative infinity to that first root on the number line, that's going to be negative. From the last root out to positive infinity, that's going to be positive in this case. So I already have two signs for my intervals. Okay, and this is the power of using the end behavior with the multiplicities. Okay. For those of you that prefer an algebraic approach or a computational approach, we can use a sign chart. So we have the interval negative infinity to negative 1. We have the interval from negative 1 to 1. And then we have the interval from 1 to infinity. So the roots divided up the number line into these intervals. Now, x plus 1 was one of our factors. When I put a test number in of negative 2, I get a negative value for the interval negative infinity to negative 1. When I put in 0 to x plus 1, I get a positive value. So that means from negative 1 to 1, the factor x plus 1 is going to be positive. From 1 to infinity, I use the test number of 2. When I put 2 in, 2 plus 1 is 3, that's a positive. So the interval from 1 to infinity will be positive values for this factor of x plus 1. When I do the next factor, x minus 1 squared, those are always going to be positive because whenever we square a real number, we get a positive result. That's not, as long as we're not squaring 0. So now our polynomial, which is the product of these two, will say I have a negative times a positive, that's negative. A positive times a positive is positive. And again, a positive times a positive is positive. Now what we notice here is that the end behavior and the multiplicity of the roots told me exactly the same information. End behavior told me that my first interval, my farthest left interval was going to be negative. My farthest right interval was going to be positive. The multiplicity said that I'm going to change sign as I move across negative 1. So I went from negative to positive. The multiplicity told me that positive 1 had a even multiplicity, so it was going to bounce. It was not going to change sign. So as I moved across the root of positive 1, I went from positive to positive. So the multiplicity and the end behavior are telling me exactly the same thing that the sign chart is telling me in this bottom row. Now our fourth step is to report the solution. So we're going to use interval notation. So here's my original inequality, x cubed minus x squared minus x greater than negative 1. It's going to have solution negative 1 to 1, union 1 to infinity. We have to skip 1 as a root because when I put 1 in, I get 0. Or actually, in this case, I actually get negative 1. Negative 1 is not bigger than negative 1. Negative 1 is equal to negative 1. So that's the comparison principle coming in. But we have a strict inequality, which means we are only interested in where things are larger than negative 1. So I have to exclude 1 here because it makes it actually equal, and I don't want that. And on this last slide here, we have a graph of the situation. Here we can see the open circles at the location of negative 1 and positive 1 for the roots to the polynomial x cubed minus x squared minus x plus 1. We have the horizontal line y equal negative 1. We see the intersection points. We leave them open because of the strict inequality. And we have the graph of x cubed minus x squared minus x always above the line y equal 1 over exactly the interval that we described previously, from negative 1 to positive 1, and then from 1 to infinity. We are above that line. And again, we have to omit negative 1 and 1 because that makes it equal to, and we are only interested in where it's bigger. Thank you for your time and attention.